Now that we know the derivative is going to play a very important role for us in calculus, even though the definition of the derivative is doable, we can find the derivative function using that definition. It's generally algebra intensive and super time consuming. So what mathematicians have done is they've come up with rules for finding derivatives that save a lot of time, where we can get down to finding the derivative and down to using it in our calculus work. Make sure you take good notes for all of the derivative rules that are coming your way over the next several lessons, and you're going to be responsible for knowing them. So again, whatever that process looks like for you, make sure you get these derivative rules in between your ears so that you can use them on quizzes and exams. The first rule we're going to look at is called the constant function rule. We're not going to verbalize it that way. We're going to recognize that if we have a function, f of x equals k, where k is a constant, then we are in the plane, the xy plane, and we have a horizontal function, a horizontal line, y equals k, that intersects the y-axis at the constant value, the real number value, k. Well, remember, the derivative is the slope of the tangent line. The slope for any constant function, any horizontal line, that slope is always 0. So we shouldn't be surprised that the derivative of a constant function is 0, and that's how we're going to verbalize that. The derivative of a constant is 0. The next one is called the identity function rule. We already talked about what the identity function is. When I put in an x value, it gives me the same value back. This is the identity function. It is the parent line function, y equals x. So for this one particular function, f of x equals x, again, we're in the plane. We have the parent function, y equals x, and we know that that is a line of slope 1. So again, we're not surprised that the slope of the parent linear function, y equals x, is 1. If we are given the function f of x equals x, and we are asked to find the derivative function, now we don't have to use the definition of the derivative. We use what we know from the derivative rules, and we say that that slope is 1. This rule is verbalized as the derivative of x is 1. So there are your first two derivative rules. The constant multiple rule. This follows from what we know from the main limit theorem. Let's say that k is a constant and g is a differentiable function. In other words, g prime exists. If our function is defined to be a constant times a function, then we can factor that constant out front. Again, constants pop out front. A lot of times it's much easier just to pop the coefficient out front and then get to the meat of what's going on and take the derivative of that function. So constants pop out front. There's another rule that we can use. The power rule. If we have a function that is defined to be x raised to some power, here it says where n is a positive integer. We're going to see a corollary by the end of this lesson that says n can be any real number. If we have a function defined to be x raised to some exponent, x has an exponent. This is a power function. not an exponential function, but a power function. So we're going to use the power rule. This is what we do to find our derivative. The power rule tells us to take the exponent, there's the original n we were given, and pop it down front. F prime of x, we take the exponent, pop it down front, copy down our x, and then reduce that power by 1. For instance, if f of x equals x cubed, the power rule tells me f prime of x equals, here's n pops down front, copy down my x, and reduce n by 1. There is the derivative for x cubed. It is 3x squared. We will use the power rule a lot. You're going to see the power rule so much that you will just internalize it. It's not even something you will have to memorize. The sum and difference rules. Just as in the main limit theorem, if I have a function that is defined to be the sum of two other functions, the sum rule says the derivative of that sum is the sum of the separate derivatives. So h prime of x, using my example, would be f prime of x plus g prime of x. We verbalize this as derivatives break up over addition. Just like our limits broke up over addition, derivatives do as well. You can see here we have the same thing going on for difference. So we verbalize that derivatives break up over addition and subtraction. We just copy down whatever the operation is, and we take the derivative of the terms that are on either side of that mathematical operation. We have all of these rules that we just saw, so let's see if we can apply them. Let's work some examples. Find f prime of x if f of x is 2x to the negative 2. Well, there's a couple of rules that I can use here. The first one is constants pop out front. I am going to take 2, pop it out front, and then take on the rest of my function. Remember, this is k times g of x. So I pop that constant out front, and now I need to find g prime of x. That is a power term, a power function, and it tells me that my power pops down front, copy my variable down, and reduce my power by 1. Negative 2 minus 1 is negative 3. I could clean this up. Negative 4x to the negative 3 is the derivative for f of x. It is how I would find the slope of the tangent line for any x input value on the f of x function that they just gave me. Let's look at the next example. Find f prime if f of x is 100 over x to the 5th. Well, I don't have a quotient rule. Be very careful. We haven't looked at the quotient rule yet, but we recognize that we can write 1 over x to the 5th as x to the negative 5. We're going to use some algebra before we use any calculus. I do want to make a point. We are going to see this most especially when we see the quotient rule. The only time you are allowed to change from a quotient to a product is when your numerator has no variables. We will revisit this when we get to the quotient rule. But for now, I don't want you to get in your head that anytime you see a quotient, you get to turn it into a product, and this is a product. It is a product of some constant times a function. So we're back right where we were in the previous example. This is the only time that you can turn that product into a quotient. If your numerator has any variables in it, you cannot. You must use the quotient rule, which we'll get to in the next couple of lessons. So here we are, f prime of x. I'm going to pop my constant out front and just concentrate on the function g of x. The power pops down front, reduce the power by 1. If this was a multiple choice problem, then I would go ahead and clean it up, and more than likely, since they gave me f of x as a quotient, the multiple choice answer would be a quotient as well. Notice we didn't go ahead and do that here because they gave us a negative exponent. So we stopped at a negative exponent. If this was not multiple choice, you're done right there. You don't even have to distribute the 100 and the negative 5. So remember to pay attention to that. Let's work this last example. Because each of these terms has a constant in the numerator only, I can rewrite them as power terms. There is an equivalent expression for what they gave me. Now I can use the power rule since I don't know the quotient rule. So f prime of x, pop my constant out front, just concentrate on that function. The power pops down front, reduce the power by 1. Derivatives break up over addition and subtraction. So now I'm down to this term. The power pops down front, reduce the power by 1. Again, if this was multiple choice, because f was given to me with terms that are ratios or quotients, more than likely the multiple choice answers would be in that same form. If it is a free response, stop right there. That is correct. This is just an equivalent form, but it is what you would see on a multiple choice question. So you can tell, especially by this last example, we're going to see functions where we are definitely going to be using more than one rule at a time when we're finding derivatives for our functions.